All right, so for question number 4, we got a pole vaulter with a mass of 56 kilograms. In the pole vault, you are trying to convert the kinetic energy of your run actually several times throughout the vault. Okay, first you build up your kinetic energy. Then you plant the pole, okay, and the pole bends. Right? In fact, it bends more on one side than the other. If you have it the wrong way, it snaps. I've seen it happen. It's ugly. Okay, so you plant the pole, and when you bend the pole, you're converting your kinetic energy into elastic potential energy stored in the pole. Okay, the better you do that, the higher the pole will fling you up. Okay, so that elastic potential energy will convert back into kinetic, and then that kinetic will turn into gravitational potential as you increase your height. Okay, so what we're basically just looking for is, okay, how much of the kinetic energy that the pole vaulter has on the ground turns into potential energy as they go over the bar at their maximum height, right? So what is her maximum height she can expect to attain if her approach speed is 8 meters per second? Assume the center of mass of the vaulter is 0.850 meters above the ground. All right, so we are going to say, since we don't know otherwise, that the initial energy is going to equal the final energy. So that's going to mean initial potential plus initial kinetic equals final potential plus final kinetic. So we'll have m times g times h initial plus 1/2 mv initial squared equals m times g times h final plus 1/2 mv final squared. All right. Are any of those 0? Yep. At her maximum height, she will no longer be moving. I mean, that's simplifying it. She's obviously moving a little bit in order to reverse the bar, but they don't give us that speed, so we assume it's 0. Well, except that they told us the center of her mass is this high above the ground. Normally, yes, I would agree with you. We'd say the initial height would be 0, but because they specified it's her center of mass, it's 0.850 meters above the ground. Okay. All right, so that's the information we know. We are just trying to find her maximum height. Do I need her mass for that? I don't. They gave it to me, but I don't need it. And I don't like having things on there I don't need. Right? So all I have to do to find H final is bring G over. So I divide both sides by G, and I'm looking for HF. So I'm going to have 9.81 times 0.85 plus 1/2 times 8 squared. Okay, that's her speed. And then I'm going to divide that by 9.81, and that should give me the maximum height of her vault. All right, so we'll have 9.81 times 0.85 plus 1/2 times 64, okay, divided by 9.81. All right, 4.1 meters. That is very respectable, okay, as a pole vault. Right, like that would be basically Olympic caliber pole vault. Okay, 4.1 meters is pretty high. You may. Okay, everybody with me on that one? Okay, is that any different than the roller coaster questions? It's not. Okay, they all work pretty much the same. All right, I want you guys to practice a few of those here for now, because we've got about 20 minutes or so left in class. I'm going to have you practice some out of the electronic workbook here. Okay, so we're starting here, guys. The bottom of page 6, conservation of energy worksheet. They start out pretty simple, like initial potential equals final kinetic. Like they start out really easy. Okay, but they'll get more complex as we go. There's only 6 of them. Okay, you'll probably get those done before the end of class. All right, so for number 1, we have a heavy object that's dropped. Okay, if it's dropped, what kind of energy does it have initially? Just potential. All right, so we're going to say EI equals EF, but we know we only have potential energy initially. Okay, if this object reaches a speed of 3.2 meters per second as it hits the floor, from what height was it dropped? Okay, when it hits the floor, it only has kinetic. Okay, and that would be our final there. It's heavy, but I don't know how heavy, but it doesn't matter because I don't need to know. Okay, it's just falling due to gravity. So all I'm doing is solving for HI. Okay, so I'm just going to bring G over here. Okay, and that'll solve for HI. So that'll be 1/2 times 3.2 squared divided by 9.81. Okay, and that should give us 0.52 meters. Yeah. Okay, any other ones? 6. All right. So in this one here, guys, we have someone exerting a force, okay, over a distance. What are they doing? Work. All right. That work, if it's a bow and arrow system, that work will become what? Energy, right? It'll become potential energy stored in the bow, and then it'll become kinetic energy in the arrow after that when the arrow does work on the bow. Okay, so what we can say then is that work, okay, is the change in kinetic energy of the. So I threw a work energy theorem question into the conservation of energy worksheet just to see who was awake. It's a mean trick, but okay. So we got a force times distance situation here, changing the kinetic energy of the arrow. Okay. We're only going to worry about the final because its initial kinetic energy will be 0. It's just sitting in the loaded bow. Okay, so I'm just looking for its speed when it leaves. So I'm going to divide both sides by 1/2 of m. Okay, and I take the square root of that, and I'll have my answer. Okay, all right. Tomorrow's Tuesday. Tuesday's quiz day. Be ready. There'll be one.